Here we're going to look at constructing a confidence interval with sigma unknown. So this is the major difference when you construct confidence interval and perform hypothesis test, whether you know sigma or not. So here, sigma is unknown. Since S is an estimate for sigma, we now estimate the standard deviation of the sampling distribution of sample means to be S over the square root of n rather than sigma over the square root of n. Now remember, when we use the SDSM and when sigma is known, our confidence interval, we take our sample mean, x bar, which is our best estimate from mu so far, add or subtract that margin of error, which was z star times sigma over the square root of n. Well, now the only difference is with sigma unknown, we still have x bar, but now we're going to use something called the t distribution rather than the z distribution. So we're going to find a critical number t star rather than z star. And rather than use sigma, we're going to use s. Because the whole theory here is that we do not know sigma. So we're using s, the sample standard deviation. Now with the t distribution, remember there's that degrees of freedom, which was just n minus 1. So whatever your sample size is, subtract 1. And that's how you look it up in the table, which we'll get to again. Okay, so in that first example, we read the question. The mean commute distance for a simple random sample of 35 college students is 12.6 miles with a standard deviation of 4.1 miles. Construct a 90% confidence interval for the mean commute distance for all students at the college. So the mean, that'll be mu for all students. Okay, so when we read that question, you have to make the distinction of whether or not we know sigma. So when you read this, that sample of 35 students resulted in this mean of 12.6 and this standard deviation of 4.1. So that implies that this 4.1 miles, that's an S value, your sample standard deviation, rather than sigma. Before, what they would have said would have been assume that sigma equals 4.1, or assume the population standard deviation is 4.1. Well now, because of the way this is worded, we're taking the fact that 4.1 miles is a sample standard deviation rather than a population standard deviation. Okay, so we're going to use the t star rather than the z star, and s instead of sigma. Okay, so we have to look up the t star value with 90% confidence interval with 34, because n minus 1 degrees of freedom. So when we try to find 34 in our table, well, that's between 30 and 40. So you go to the smaller degrees of freedom because that allows you to be more conservative, basically resulting in a larger t star value. Okay, so with a, was it 90? Yeah, 90% confidence level. So we have 90% here. We go up to 30 degrees of freedom, which is 1.697. Okay, so rather than using the z-score of 1.645, we're using 1.697. It's a little bit larger, which means you're going farther away from that center. Okay, so as far as the work goes, the work is exactly the same as before. Okay, so we have our formula, x bar plus or minus t star times s over square root of n, and now it's just plugging into that formula. You take your estimate for the population mean, which our best estimate when we take that sample is the sample mean, which is 12.6, and then add or subtract that t star times s over the square root of n. And the good news with using s rather than sigma is that because it's a standard deviation, even if you don't catch in the question that you're looking at a population or a sample standard deviation, you're going to put it in the same place anyway. Okay, so because S and sigma are in the same place in the formula, what you're going to miss is that T star or Z star value. Okay, so you would, if you thought that was a population standard deviation, you would have had 1.645 here instead of 1.697. And that will be several points off when I grade something, because that's like the major concept here, is that we're using the T distribution rather than the Z, because we do not know sigma compared to knowing sigma. Okay, so your interval, you calculate it the same way as before. You get your margin of error, 1.176. And I didn't tell you what to round to on this one, so we're not going to focus too much on that. So we end up with, we're 90% confident that this interval contains the true value of mu, the mean commute distance for all students. Okay, read the second question. And notice that you have 100 patients, so now your degrees of freedom will be 99. The mean was 5.3 days and the standard deviation is 7.6. So again, when you read that, you notice that those numbers are coming from the sample. So that means that the 7.6 days, that's a sample standard deviation S. Okay, so knowing that, construct a 95 and a 99% confidence intervals for the mean length of stay for all sickle cell anemia patients. Okay, so I suggest you pause the video and read through the question again if you need to, and I'm going to go and show the answer for the 95% interval first. Okay, so try it and pause the video, and here's the answer. Okay, so with 95% confidence interval, and we have 99 degrees of freedom, so 95% confidence level with, we're going to go up to the 80 degrees of freedom, 1.990, rather than 1.96 for the Z distribution. Okay, so we have 1.990. Okay, which they're fairly close to each other, but because it was from a sample, and when we're using the sample standard deviation, we need to allow more room into our estimate. Okay, so we're using a larger value there for T. Okay, so that's where that 1.99 goes. Okay, so we're 95% confident that the mean stay for all sickle cell anemia patients is contained in this interval from 3.79 days to 6.81 days. For a 99% confidence interval, well, to be 99% confident, now we're using 99 right here, and then going up to the 80 is 2.639. Okay, so that's your T star value, your critical number, 2.639. And then you go through and finish off the interval just like before. Okay, now the other kind of question that we get to on these is, rather than reading a question and it tells you the mean is this and the standard deviation is that, well, now you're just given a list of data. Okay, so this is another way you can be presented the information. Okay, rather than I'm telling you the mean and standard deviation, now you have to find it yourself. Okay, so you put your values into your calculator and calculate the sample mean and sample standard deviation by doing the 1-bar stats on list 1. And when you do that, you end up with 105.58 for the sample mean, and then S is 7.763. And I'm not going to go through those steps because you should be able to use your 1-bar stats to find those values. And I just want to point out that your calculator does also give you sigma, but that's if this was all the values here. So meaning if those were all the movies, but that 12 movies is just a sample of movies. Okay, so even though it gives you sigma, your calculator doesn't know whether that's a population or a sample because it's just seeing numbers. It's not understanding the context. So we know we're going to use S for the sample standard deviation. Okay, so now the question is the same as the other ones. Construct a 95% confidence interval, knowing that the sample mean is 105.58 and the sample standard deviation is 7.763. Okay, and again, with the rounding, here I say round to the nearest tenth. Okay, but the rounding isn't the point of doing this. It's the process of it. Okay, so rounding to the nearest tenth, generally you don't round till the very last step. So when you substitute your values in, you want to leave like 2 or 3 decimal places before you round. Okay, so here's your sample mean, 105.58. Now your t-star value is 2.201. So that's 95% confidence interval. And there are 12 values in the sample size. So that's 11 degrees of freedom. So a 95% confidence level with 11 degrees of freedom. Okay, that one shows up right here. So 95% confidence, that gives you 2.201 in the table. Okay, and then you substitute your sample standard deviation divided by the square root of n. So you end up with this interval. Margin of error, 4.93. Okay, so we're 95% confident that this interval contains the true value of the population mean length of movies. So between 100.7 minutes and 110.5 minutes.